Okay, hey everyone. So we're really excited to be here today to talk to you about fast, flexible, and scalable data loading for ML training using array data. So first, just a little bit about us. I'm Stephanie, and this is Scott, and we're both software engineers at Anyscale working on the array data and core teams. And we're really excited to be here today to talk to you about some of our open source work. So hopefully by the end of this talk, you'll understand the role of array data in ML training workloads, how the design of array data has an advantage in this kind of workload, and also looking at some performance benchmarks comparing array data to some other open source data loaders that you may have used in the past, including PyTorch DataLoader and tf.data. Okay, so first, what exactly is this data loading problem? Well, in data loading for ML training, generally what you have is, sorry, I think the slides, oh, okay. The data loading for ML training setup basically looks something like this, where you have some GPU trainers in a cluster, and you have a data set that's stored either on local disk or cloud storage. And what you want to do is, here you actually want to load all of your data into memory and stream that to your GPU trainers. Now there's a few different things that make this challenging to do. So first of all, you want this data loading process to be fast, because as soon as one of these batches of data becomes ready for training, you want to load that into the GPU as quickly as possible. And by the time the GPU is ready again to process the next batch of data, you want that batch of data to already be ready in memory. And so basically what you want to do here is actually overlap that data loading process with the GPU training. You also want this to scale. So here we have this large data set that's stored, say, on cloud storage. And we also have a cluster of multiple trainers. And so what that means here is that we can't necessarily just fit all of that data in memory. We actually want to stream that data set through memory into the GPU trainers. And in this case, because we have these multiple GPU trainers, we also want to, in some cases, to actually transfer that data over the network. So say between cloud storage and each GPU trainer. And then finally, we want this process to be flexible. So today, the preprocessing that you want to do during this data loading step is becoming more and more complicated. And so you can have data that might have different storage locations, different modalities like text or audio or video, and also different preprocessing functions. And those different preprocessing functions will also have very different resource requirements. So some might be memory intensive, while others are CPU intensive. And then, of course, there's also the data ordering. So in some cases, you might want to randomly shuffle the data set. If you have multiple trainers, then you want to partition the data set across your trainers evenly. So what that looks like here, putting this all together, is that as these batches of data get processed, we want to load them into the GPU trainers as quickly as possible, and also balance the data across the trainers. And in the background, we want to continue loading more data into memory while these GPUs are training. So let's take a look at how array data can meet some of the goals in this workload. So first of all, array data is fast. Here, this is showing a plot of GPU utilization in a 16-node array cluster. And here, we're just training ResNet 50 on an S3 data set with a bunch of raw images in it. And what we can see here is that we're able to keep the GPU utilization at close to 100%, even for this relatively small model. One of the reasons we're able to do this is because array data is actually loading all of this data from S3 in the background. And we're able to scale this out to keep up with the GPU utilization by parallelizing these reads from S3. And then finally, one of the most important things here is that array data is actually controlling how much memory is getting used during this process. And so you can see that the memory usage here on the CPUs actually stays about constant throughout the training job. And so the things that make this possible, so there's two important things here. One is the fact that we're using streaming execution. So this is a 10 terabyte data set that's not going to fit in memory, which means we're actually streaming that data set through the cluster memory and to the GPUs. We're also using Array's shared memory object store here, which allows us to read this preprocessed data with 0 copies. Okay, so that was a little bit about how array data can give you the performance that you need. And later in this talk, Scott will also show you some benchmarks looking at the scalability of array data. And two of the most important things here are, one, the ability to use heterogeneous clusters made up of both GPU nodes and CPU-only nodes. And that's what's going to allow us to scale out even further past where most data loaders today can do. Array data is also flexible. So the in-memory format that we use is standardized on Apache Arrow. And this is an interoperable format that makes it easy to work with other popular data formats like NumPy and Parquet with different data modalities such as text or video or audio, and also with all of the popular model frameworks like PyTorch, TensorFlow, and Hugging Face. Array data lets you build these arbitrary data preprocessing pipelines, and it comes with a simple query planner that allows you to do things like group by. Okay, so today we're already seeing some early traction among array data users with people using array data to scale out their data loading. So in many cases, we're seeing that the reasons people are using it are to improve the performance of their data loading stack so it can keep up with their GPU utilization, to scale out to larger and larger data sets, and also to improve the iteration speed, looking at different data set and model experiments. Now, before we talk more about the design of array data, I also want to give a little bit about some of the features that array data has compared to other popular data loaders. So one of the main differences that sticks out in the implementation is that array data is built on array core. And that gives us a bunch of these generic distributed execution features basically for free. So we'll take a look at some of those later when we do a deep dive in the design. Array data also has really great data format flexibility. So I mentioned earlier that it's built on Apache Arrow. It actually also allows you to write out your preprocessed data sets. So you can do things like convert easily from an image data set to a Parquet data set. And you can even use it for batch inference, which we'll see in some later talks in the summit. Array data gives you auto-partitioning. So you can choose between statically partitioning your data set before training starts, or dynamically doing it, so letting array data decide where data should go based on when it's ready. Scott will show you some benchmarks later on, looking at some of the more advanced speed and scale features that array data has. So that includes being able to cache your data set at any stage in the preprocessing pipeline, as well as being able to use these heterogeneous clusters made up of both CPUs and GPUs to scale out even further. And then finally, array data has some other features here that become really useful once you are starting to scale out to even larger data sets or larger clusters. Now, for today, we'll be focusing mainly on these first rows, but feel free to ask us afterwards about these other features. Okay, cool. So first, I'll talk a little bit about the array data design and how it compares to some other multiprocessing-based data loaders. So first, taking a look at the API and array data. So what you get here is some basic read APIs that let you read from popular formats. So in this case, we're reading from raw images stored in S3. And here we're applying this this UDF to each image in that data set. So in this case, we're randomly cropping and flipping each image. From this, we can then take this data set, which is executed lazily, and we can create an iterator. In this case, we're iterating over torch batches. And so here is where you might insert your training code. And in practice, what you would actually do here is use array_train to execute this training loop. But just for the purposes of this example, you can kind of think of this as the main dataset API. OK, so there's a few different design decisions that are happening under this API. So there's, first of all, how are the workers implemented for the data loading? How does data get passed from the workers to the trainers? And then how does work actually get assigned to those workers? So to understand where array data does well here, we can actually look at how, how multiprocessing-based data loaders work instead. All right, so in multiprocessing data loaders, of course, the workers are implemented with the Python multiprocessing library. And so what that means here is that on this node, we have these 2 GPUs, but each of them is only going to have its own data loader. So we can't share a data loader between the different GPUs. So one thing we might do here is take the CPUs that are available, maybe give each GPU 2 of those CPUs. And so these multiprocessing data loaders will start 2 different Python processes in the background to load and preprocess the data. The data in this case is going to get passed directly from these multiprocessing workers to GPU memory. And one of the most important things here is that the work here actually gets assigned to the workers before any of the training starts. So what that means is that you actually have to do quite a bit of manual tuning to achieve certain things. So for data partitioning, for example, you'll have to decide which data is going to go to which trainer before any of the training starts. And for things like performance, you'll have to think about how many workers to use for each data loader. So you want to use enough workers that you get performance that keeps up with your GPUs. But you also don't want to use too many workers because then you might run out of memory. So in the Ray data design, we're actually going to depend on Ray Core to do a lot of these generic multi-core distributed compute things for us. And then Ray Data is going to build on top of that to give you some of these data loading specific things. So here, the cores here will actually be managed by Ray Core. So Ray Core will start workers as necessary to keep up with the work that's being assigned. Ray also has this shared memory object store, which in this case acts as kind of this buffer between the workers and the GPU memory. And then finally here, the most important thing is that the work here is actually assigned to the workers as these smaller tasks. So a task might be some small partition of your larger data set. And then these task outputs are going to get spread on the fly to the GPUs based on which data is ready first. So here what that looks like is Ray Data is going to assign one of these tasks to each worker. And as these workers produce results in the shared memory store, so this might be a series of batches, we're going to feed those to the GPUs as they become ready. And here now we can actually free up those workers for additional tasks. Meanwhile, those other tasks are going to finish. So once the GPUs become ready again, they can just get the data that they need from the shared memory store. Okay, so here there are actually a couple overheads that we're adding compared to the multiprocessing only design. So one thing, for example, is that we have to copy that data from the worker memory to the shared memory first. We also have a small amount of Ray Core task overhead, so less than 1 millisecond for each of those tasks. But in return, we get a bunch of really nice features for free. So we can automatically partition this data set across the GPU trainers. We can have the Ray Data scheduler actually control the execution to dynamically load balance the work and also make sure that the total memory usage stays controlled. We can also recover from failures here without having to restart. Because here, if one of those individual tasks fails, we can just restart that task without having to restart the whole thing. And so basically here, we're getting a lot of these distributed features from Ray Core for free. And so just to show a little bit about how that works, here is the exact same setup as before, but now in a distributed setting where the GPU trainers are on different nodes. So same as before, the Ray tasks are going to create these preprocessed results. And Ray Data, in this case, is actually going to route these batches based on where the nearest GPU is. So here, we can decide to actually move the preprocessed batches to the nearest GPUs. The other nice thing that we can do here is we can actually cache those Ray Data sets by using this ds.materialize call that's provided by Ray Data. And here what that looks like is actually very similar to the previous setup. The only difference is that we're not cleaning up this data that's in the shared memory store as we go. And so what's cool here is that we can actually use this setup to cache the data at any stage of the preprocessing. And Ray Core will even automatically spill this data to disk if the object store becomes full. And that allows you to avoid out-of-memory failures. And then finally, the last thing I'll show is how we can use array data to scale out with heterogeneous clusters. And this is actually, again, the same setup as before, but now there's no GPU on the second node. And so what we can do is actually still execute on the CPUs on this node, and then transfer this data over to the GPU node in the background as the training continues. OK, so next, Scott will walk you through some benchmarks, looking at how that works out in practice.
Awesome. Yeah, so now I'll be talking about some of the benchmark results comparing array data to the other data loading solutions that we've discussed. So for this benchmark, the primary task that we'll be using is the MLPerf image classification task, which is essentially just reading images and training a ResNet 50 model. And for this benchmark, we're going to be comparing array data with PyTorch DataLoader. And the high-level steps that we're going to be doing on this benchmark are first to load the images from S3, then applying a preprocessing function to each of the images, and finally reading in those images with a PyTorch trainer. And for these benchmarks, the things that we want to highlight from the array data side are its scalability, support for heterogeneous clusters, as well as dataset caching. Right, so let's take a look at the implementation, comparing array data and PyTorch DataLoader. So for the first step, we're going to be loading these images from S3. With array data, you can simply use the read images API and just pass it the S3 path. For PyTorch, we found that to use the built-in S3 data loader, we had to implement our own custom file loader to make things work in a distributed setting. Second, we apply a preprocessing function to each of the images. Again, with array data, it's very simple. We can use the built-in map API to apply the function to each image. On the PyTorch side, we have something very similar where you can use the map function to apply whatever UDF over each row. And it's important to note that on the array side, we have a query optimizer that Stephanie mentioned before. What this does is it basically fuses certain steps in the dataset pipeline, if possible, to optimize streaming execution. So in this case, what we'll do under the hood is we'll be combining the read images and the preprocessing function into a single step. But the user doesn't need to worry about this, as array data does all of this under the hood. Finally, for the last step, we're going to be ingesting these images with raytrain. We're going to be using the raytrain torch trainer. And just as a quick summary, raytrain is a distributed deep learning library built on top of raycore. And so it provides a lot of the similar advantages that we get from array data as well, such as flexibility, scalability, and fault tolerance. And for this, we're going to be using the torch trainer. It's very simple to use as well. We simply pass it a function that does the train loop on each worker. And then within this function, we're just going to be iterating over either the array data sets or the torch data loader. Cool. So now let's take a look at the scalability results comparing array data to torch data loader. So for this benchmark, we're comparing we're increasing the number of nodes from 1 to 16 to see how array data does against torch data loader in reading images from S3. In terms of the data set, we're going to be using the ImageNet data set stored as raw images on S3. And we'll have each trainer read about 10 gigabytes of images. So for example, in the 4-node case, we're going to be reading about 40 gigabytes of data in total. And so in the 1-node case, we can see that the torch data loader does outperform array data. This is due to several overhead from the array core side that Stephanie mentioned before, such as writing to object store. And then, but as we scale up the number of nodes, we see that array data is able to keep up with torch and even outscales torch data once we get to the 16-node case. Taking a step back, I just wanted to highlight some of the pain points working with PyTorch versus array data. In terms of the data loader, we found that, again, the implementation of the existing or the built-in S3 data loader was not sufficient in order to work in a distributed setting. And so we built our own file loader on top of this in order to make things work. In addition, we had to do some tuning with the number of workers with the torch side, because we found that when we just used the torch out of default, or by default, we found that the number of workers was too small and we were not getting full GPU utilization. And so when we increased the number of workers, we actually ran into GPU out of memory issues. And so we had to do some tuning of the number of workers in order to get things to work. Finally, another benefit of using rate data over Torch is that we can do the partitioning of the data automatically, whereas on the Torch side, we had to decide which partition of the data will go to each worker. Next, I want to go into one of the edges that rate data provides, which is support for heterogeneous clusters. And so as we mentioned before, rate data is able to make use of clusters with both CPU and GPU nodes in order to maximize efficiency and usage. And so in this case, we see with the CPU nodes, which can handle the data processing, as well as the GPU nodes, which handle both the model training and the data processing, rate data is able to make use of both types of nodes in order to maximize throughput. And it's important to note that heterogeneity is not currently supported by other open source data loaders that we discussed, such as PyTorch DataLoader, Hugging Face datasets, and Mosaic streaming datasets. And so going back to our first benchmark, we now added some extra CPU nodes into the 16-node case. And so one thing to note here is that there's no code change here. It's simply a configuration change and adding additional machines. And with the extra CPUs, we're able to maximize throughput and get almost double the output that we saw in the 16-node case without using these extra CPU nodes. Finally, the last thing I wanted to talk about was rate data's ability to cache flexibly. And so it's able to cache the data set at any stage of the preprocessing pipeline in order to speed up data loading. So we've implemented two variants of caching here. On the left, we're caching the input images. And so before we do the map, we're saving these images. And then for each iteration over that data set, then we'll be applying the preprocessing image. So we get a slightly different image each time we go over the data set. On the right-hand side, we're caching the data set after we apply the preprocessing. And so we'll have the exact same data set for each iteration over the data set. And then in comparison to other data loaders, the data loaders which rely on multiprocessing don't have support for in-memory caching. They currently only have caching for like writing to local disk. And so comparing the results from just the caching and using heterogeneous clusters to the first benchmark, we can really see how much performance we can squeeze out of Ray. So taking a look at just the results from the caching, in blue we have the results from the 16-node case in the first benchmark without any caching. And then in purple, we have the variant where we're caching raw images. So in this case, we don't see much of a speed up because we not only have the additional overhead of caching the raw images, we're also still running the preprocessing function for each iteration over the data set. However, in the case where we cache the preprocessed images, we see almost a 7x increase in throughput. And of course, this comes from the fact that we're caching these images which are already preprocessed, and so we don't need to apply that preprocessing function each time. Finally, we can combine this with using heterogeneous clusters, and we see that for the no caching and the cache raw images cases, we see an increase in throughput. And the extra CPUs that we're adding here alleviate some of the extra overhead that we were discussing before. Finally, I wanted to go over some of the key features related to machine learning that are relevant to rate data, or that are on rate data and Anyscale. So just to highlight some of the features that we haven't discussed yet, we have the ability to save a data set that's already in memory. For example, you may want to process some data and then save that into a different format. And then another benefit that we have is this ability to recover from out-of-memory failures. And on the Anyscale side, we have dedicated APIs for video and audio files, which are becoming more and more relevant today, as well as support for local and global shuffle, and faster reads from data stored on cloud. Awesome. To recap, rate data is a fast, scalable, and flexible solution for ML data loading, which is unmatched by other open source data loaders. And I also wanted to highlight a few related talks coming up at Ray Summit. So later today, we have a talk from our Ray Train team going over just a deep dive of Ray Train. And then we have another talk today from Instacart on how they use Ray to scale their computer vision models, as well as 2 talks tomorrow, one going into a deep dive of streaming, Ray data streaming, and another one going into offline batch inference using Ray data. So yeah, hopefully you can check those talks out. We've also included a few links to our resources, including Ray data documentation, as well as a doc specifically for the integration between Ray train and Ray data. Yeah, thank you so much for coming.
Great talk, fantastic results. I had a question about the applications rather than training. You focused a lot on training, but you also mentioned saving data sets for kind of late offline use, not materialization on the fly, but something that is actually cached for others to use later. And I'm curious, what is your thinking how Ray data can power that sort of applications where you just want to process data? Because like if you have sufficiently rich set of operations beyond like simple map functions you showed, maybe you have group by, maybe you have a join, right? At this point it becomes a generic data processing engine. And there are other talks, for example, like I was on another talk about exabyte data processing, and it seems to be really related. Like, have you guys been thinking about that sort of applications going deeper into that generic data processing?
Sure. Yeah, I can answer that question. So I think the question is basically about the fact that like Ray data, as we talked about it here, actually has a number of features outside of just the data loading problem. And how are we thinking about sort of generic large-scale data processing in our roadmap? Is that right? Yeah, so I think for now, our focus right now is mainly on looking at cases where we think that the data processing for ML applications story is not yet well supported by other solutions out there. And so that's why we have like such a big focus here on looking at data loading problems. I will say that I think, in general, we're seeing that this data loading problem and the data preprocessing problem is becoming more and more complicated for people. And so I wouldn't say that it's on our immediate roadmap, but definitely we do want to help people work with their data sets more easily. So some of the things that people are starting to do is actually using Ray data to deduplicate and randomly shuffle their data sets offline. And so we're looking at some of those kind of more specific use cases where looking at operations that you would commonly want to do on a data set meant for ML. I think, yeah, maybe you next.
There's a line somewhere in the Ray docs that when you read enough array from object storage, it doesn't get copied. Does that work for anything else, like torch tensors?
Yeah, I can answer that question. So the question is about basically what data formats does zero copy work for? So I think unfortunately there is a limitation with Torch where Torch tensors actually cannot be read zero copy. But what we do instead is actually store things as NumPy or Arrow, and then you can convert with zero copies to a Torch tensor. So that's actually exactly what Ray data does under the hood. Yes?
Are you able to use pinned memory and share in the background?
Are you able to use what? Sorry?
Pinned memory pushed to the GPU?
Did you say streamed memory?
Pinned memory.
Oh, pinned memory. Oh. Do you want to answer? Or?
I'm not sure.
Oh, sure. Yeah, I can. So are we able to use pinned memory? So yeah, basically what the Ray data, that iterator that you saw, what that does is it actually will move the data that you're reading to GPU memory in the background. So there's actually a parameter you can use also that specifies how many batches to prefetch. And yeah, so that will pin it in GPU memory for you. Sorry, could you repeat the question? So it's, yeah.
Like, we want to adopt Ray data, but sometimes we saw like some Python classes actually cannot be directly, the object cannot be put in Ray data. So we have to do some refactoring, but do you have any plan, like just publish an API, something?
I see. Yeah, so I think the question is about kind of supporting arbitrary Python objects. Is that right? Or
Like have a more like a restriction, like something like a similar, probably similar to code box. So if you define it according to your API, then data class actually similar to Python class, but it's guaranteed it can be compatible to array data.
I see. I see.
This is related to like serializability of, I think, like objects that get put into array objects, right? Yeah.
Yeah.
Array data is a bit more restricted because like essentially it's more like a data frame, so it's a bit more restricted.
Yeah, so I think unfortunately making serialization work fast and general is a pretty difficult problem, I would say. I think, yeah, if you have like specific use cases, feel free to follow up with us on GitHub afterwards, because I can't promise that will work for sure, but there should be a way around it. So yeah, I mean, I think like being able to have custom serialization is definitely something that we care about.
Yeah.
Yes? Or are we out of time?
I think we're coming up on time, but
Okay.
please feel free to contact us after. We'll be happy to answer any questions. Yeah.
Yeah.